Hello everyone and welcome. So this week we are going to be talking about chapter 12, static equilibrium. And elasticity and fracture is actually not in your reading assignment, but I will show it anyways because I think the topic is interesting and fun. These are your problems, suggested problems. Hopefully we'll solve them tomorrow. So let me go ahead and start. So first I want to introduce equilibrium. And when I say equilibrium, I mean static equilibrium. And for this, we mean an object that is in a state in a certain configuration, stays in that configuration no matter how long time passes. And for this kind of static equilibrium, we have two conditions. The first one is from Newton's laws. Sum of all forces on the body should be zero. Since force is a vector, we need to consider sum of all forces in vectorial form. If you open this up, you'll see that each component of total force should be zero. For example, if you put your book on your table, the total force in any direction should be zero. Obviously, there is no force along this direction, horizontally, but in a vertical direction, there's like gravity, and if the total force is zero, there must be like an equal and opposite force to cancel the effect of gravity, and we know it is a normal force. And the second thing is, this condition itself is not sufficient for static equilibrium. So you can consider a situation like this. Imagine you put your ruler on the table and you pull the ruler from the opposite ends, from here and here, in the opposite directions. It's easier to see the total force in the system is zero, so this force cancels this force, but this ruler is not in static equilibrium because it's going to rotate. There is like a torque, which brings us to our second condition. For static equilibrium, sum of all torque should be zero. And I wrote this in this form. And what is important to note that this should be valid for any choice of axis. So there should be no rotation for any given axis. These are just two conditions for static equilibrium. Maybe we can go ahead and then solve an example and see this in practice. So here's the first example from your book. A chandelier is like hanging from the corner ceiling, and we want to calculate the tensions FA and FB in the two cords that are connected to the vertical cord. And the weight of the chandelier is like 200 kilograms, and we ignore the masses of strings. So the net force should be zero for static equilibrium. Then the net force in a horizontal direction should be zero, and net force in horizontal and vertical directions should be zero separately. So let's start with, I don't know, maybe I can start with vertical direction. So sum over all forces along y should be zero. So I can decompose this vector to its components. This is nicely 30 degrees. And from this figure, what I see is for this to happen, F, the force A, and it is Y component, which is equal to FA, the magnitude of FA, times cosine 30 degrees. And this should be equal to M times G. Then FA is equal to mg divided by cosine 30 degrees. Let's calculate this. 2,263. Yes, I think somebody else got the same thing. 2,263 Newton. Now this is only the first component. We also should do the same thing in the opposite direction, in the orthogonal direction. Then fx should be 0. But along this direction, so fb and fa times x are the two forces. So then fa times x should be fb, then this should be fa times sine 30. This is a little easier. This is just half of that guy, which is then fb is equal to 130, 1.5, something like that, Newton. Great. So let's talk about another example for the second condition. So here is a conceptual example from your book. So a bar in figure 5 here is being used as a lever to pry up a large rock. The small rock acts as a fulcrum, a pivot point. There's like a small rock. You may not be able to see that, but it's there. And the force Fp required at the long end, like this force of the bar, can be quite a bit smaller than the rock's weight, mg, since it is the torques that balance in the rotation about the fulcrum. If, however, the leverage isn't sufficient and the large rock isn't bulged, what are the two ways to increase the leverage? So you want to move this rock, and let's say in this configuration, it's not working. What two things can you do? Decreasing R over R, yes. So I think the idea is, so I think simple, but let's just go over it. Doesn't matter. G times R should be equal to Fp times R. Then you want to have some Fp is equal to R over R times mg. So the idea is you need to decrease this R over R to have like sufficient force to move this. So one way to do this, you can increase R. So I think in the picture they are suggesting to connect like a pipe or some extension so that you can increase the R. Of course, this is going to help because R is increasing. Or you can decrease R, or like you can just move the fulcrum a little toward the big rock. So this will also decrease R over R. Okay. So let's move on. So a board of mass 2 kilogram serves as a seesaw for two children, as shown in this figure here. Child A has a mass of 30 kilogram and sits 2.5 meters from the pivot point P, this one. And his center of gravity is 2.5 meters from the pivot. At what distance x from the pivot point must child B of mass 25 kilogram place herself to balance the seesaw? Assume the board is uniform and centered over the pivot, like here. So the forces, let's identify the forces. There's some force ma times g. There is some force mb times g. And there is some force from the board. Let's call this capital M times G. And for balance, there must be no rotation. And I choose my pivot point here. So what this means is, so MA times G times maybe 2.5 meters should be equal to So X times MB times G. So then X should be equal to, I think I can cancel G's, MA over MB times 2.5 meters. It should be equal to, I think we can calculate this, 3 meters maybe with the digit, 3.0 meters, right? Simple. Okay, let's continue. So here's another example. This is actually, I made up this example. So here's a cantilever. It's like a device that is shown in this figure. And there are two supporting points here and here. And center of gravity of this board is here. And the mass is given, or like M board times G is given to be 12,000 Newton. And we want to calculate FA and FB. So the length is like 20. There's like a 5 centimeter here. And this total distance is 30 centimeters. We can start off by saying torque must be 0. Yes. So there are like two conditions, right? So there are two conditions. One is total force should be 0. Then from here, okay, everything is in one direction. So I'm just going to write magnitude. It's only in the vertical direction. So this means, so FA plus FB should be equal to, obviously, M board times G. So the second one is the total torque should be 0. And I want to choose, for example, this point. So that means, okay, 2 FB times 20.0 meters should be equal to M board times G times, I think, 20 plus this little chunk is 25.0 meters. Then FB is equal to, let's calculate, 15,000 Newton. This is 15,000 Newton. So now I can put this back in the other equation. Just plug this in here. So then FA is equal to MB times G minus FB, which is equal to, I guess, minus 3,000 Newton. Now, okay, I found some minus here. What does this mean? Are we confused with this minus sign here? Are we okay with this? Exactly, right? This just means our assumption about the direction was wrong. So this is force FA is actually in the opposite direction. Of course, from the figure, it's not clear, but maybe it's glued here, or there's like some screw or like maybe nail. So it's just force is just pulling it down, which should be the case. Otherwise, this thing would not balance. So this will be a general thing. So in the problems concerning static equilibrium, if you find things like this, you just reverse the direction of your force and you're good to go. So here's another example. How much force must the biceps muscle exert when 5 kilogram ball is held in the hand like this, with the arm horizontal as in figure 8A, and B when the arm is at a 45-degree angle as in figure 8B. The biceps muscle is connected to the forearm by a tendon attached 5 centimeter from the elbow joint. So this little distance is 5 centimeter from the elbow joint, and assume that the mass of forearm and the hand together is 2.0 kg, and their center of gravity is as shown like here, which is 15 centimeters. I think this is the same problem, so I will go ahead and start. So I'll just look at the torque with respect to this point. And if you draw a line from this point that will go through all the other forces, you can see all forces are perpendicular because forearm is perpendicular. So let's do this. So Fm times the distance is 5.0 centimeters. So I'm choosing size centimeters here, so I should be consistent in the rest. Minus, so 2.0 kg times 15 centimeters. So I got this guy, and minus 5.0 times 9.8 times 35 centimeters should be 0. Then Fm is equal to what? It's equal to 349 Newton is what I found. Hopefully you guys found the same result. So this was A, and B. So B, when the arm is at 45-degree angle. So I'll just do the same thing here. But this time, the torque will be the distance times the perpendicular component of each force, but this is 45, so the perpendicular component is like, I guess it doesn't matter, sine or cosine 45. This guy, and this guy. So if I do this, Fm times 5.0 centimeters times, okay, let's be, doesn't matter, but let's be precise. So this is also 45, this is also 45. So this one will be cosine 45 degrees minus 2.0 kg times 15 centimeters times, okay, this guy, this is 45 cosine 45 degrees minus 5.0 times 9.8. Okay, there's like a 9.8 here. I messed up. This one should be 9.8. So let me first fix that guy. It's clear. 401.8. Thank you. 402 Newton, right? Thanks for fixing this. Good catch. So this one is also 9.8. So this thing should be 0. Okay, like, let me not go ahead of myself. So there's like times. Cosine 45 degrees should be 0. So if I look at this, all these cosines cancel. So it's actually the same equation. So Fm is equal to 402 Newton is the same. So, okay, another example. So a uniform beam 2.20 meters long with mass m is equal to 25.0 kg is mounted by a small hinge on a wall as shown in this figure here. The beam is held in a horizontal position by a cable that makes an angle theta is equal to 30.0 degrees. The beam supports a sine of mass m is equal to 28.0 kg suspended from its end, like here. Determine the components of force Fh that the smooth hinge exerts on the beam and the tension Fd in the supporting cable. I guess this force and this force. Net torque and net force are 0, yes. So how can I start? What's a reasonable route for me to find with minimal effort? Since we know M and M, we can find FTY, yes. So I see. You suggest I can start from this guy, right? Okay, let me start. And I believe you mean a calculation of torque with respect to this hinge. And so there's like mg, there's another mg, and there's ft, and there's nothing else, right? So let's do this. So total torque is 0. And from this, okay, let's call this L over 2, then mg L over 2 plus mg L should be equal to ft times L times sine theta. Right? Then I think I can cancel L's. And what I find is ft is equal to m over 2 plus m over sine theta times, times g. So then ft is equal to something like 794. Good. Yes. Thank you. 794 Newton. Now I look at the figure again. So I found this force from this component. And now I look at this component. This should cancel with this component. But not only that, there's also like the total force on the system should be 0. So maybe I can actually find this first and then this first. So this is first step. So total force is 0, then so FHY plus FTY should be equal to M plus M times G, then FHY is equal to M plus M times G minus F of Ty, and this is equal to, let's calculate this, 122.4. This is 122.4 Newton. And so in the horizontal direction, there's only this force and this force. So maybe FHX should be equal to FTX, then FHX is equal to, okay, what is it, like FT times cosine, 687.6. 687.6 Newton. Now I can calculate FH from the Pythagorean theorem. It should be equal to, okay, 698.4. 698.4 Newton. So let's go with the next problem. So a 5-meter long ladder leans against a smooth wall at a point 4.0 meter above a cement floor as shown in figure 10. So this is 4 and this is 5. The ladder is uniform and has a mass m is equal to 12.0 kg. Assuming the wall is frictionless, but the floor is not, so there's no friction here, but there's some here. Determine the forces exerted on the ladder by the floor and by the wall. We want to find this force and this force. How should I start? Any suggestions for me? Fcy is equal to mg. Okay, that's good. So let me write this. So total force along y is equal to 0. And from here you are saying mg, or maybe I can write it the other one first. Fcy should be equal to mg, and this is equal to what? 12.0 times 9.8. 12.0 times 9.8 is equal to 117.6. 117.6 Newton. What else? So I got this component. I have two more components to calculate, this guy and this guy. Fcx is equal to Fw. Fcx is equal to Fw, yes. So let's write this one too. So the force along x is 0, then Fcx should be equal to Fw. That's good. But I don't know both of these, so if I can find one, I have the other one. So mg times 1.5, okay, finding the torque relative to the top. So, okay, you want to find the torque. You mean with respect to a pivot point here? I guess it doesn't matter, right? But so you want me to choose this point as a pivot or this point? Maybe top point, that's what I understand. So let me do it this. So total torque is 0. So I'll choose the top. So this is, I think we know this triangle. This is 4, 5, 3. And I can calculate the perpendiculars like this. And this guy has a perpendicular like this. And this guy has a perpendicular like this. So somebody says floor is better, right? I agree. Maybe I can do the floor because I don't want to deal with these two forces. Let's do floor like here. This one, right? Now I only have to deal with this force and this force. I have one less thing to deal with. So if this angle is theta, this angle is also theta. So this is 90 minus theta. This is theta. This is 90 minus theta. So torque is 0, then mg times cosine theta, which is, okay, maybe I can write it. Cosine theta is what? Theta is here, cosine 3 over 5. 3 over 5 times, and the distance is, this whole thing is 5, so half of this is 5 over 2. 5 over 2 should be equal to Fw times, So cosine of 90 minus theta, which is this angle, is sine of this. So this is going to be sine theta is 4/5. I think this is times, I think 5, right? I can cancel these, this guy, this guy, this guy, this guy. Now I have an expression for Fw, which is 3/4 m times g, which is equal to this 88.2 Newton. So if Fw is this, we know from this Fc of x is also 88.2 Newton. Then Fc is, we can also carry on Pythagorean theorem to find what this is, but this is basically 88.2 times 88.2 plus 117.6 times 100. You found 44? Okay, then I messed up. Let's see where I messed up. Oh yes, I forgot this half. This half, right? Thank you. So this is actually 3/8. Okay, let's clean this up. So this is 3/8. This is 4, and this is 1. Thank you. Yes. So now I can redo the other one. Okay. This is 4.1 Newton. Let's do this. Actually, let's call it 126. 126 Newton. So I think this is all, but I want to talk about the rest of the chapter just to expose you to some interesting stuff. All right, let's move on. So now I want to, okay, we've been talking about static equilibrium, and now I want to introduce a new concept called stability and balance. So we first start with like a static system, like a system in static equilibrium, and we assume that it's like stationary, and we consider small perturbations on the system. So what does this mean? Consider a system like this, a ball hanging from the ceiling with a string. Obviously, this system is in static equilibrium because it's not moving, but I want to understand what kind of static equilibrium this is. And for this, I'm considering this. I just give it like a tiny little bit of perturbation, maybe like this. And I look at the system. If the system after this perturbation returns to its initial state, we call this kind of equilibrium a stable equilibrium. Right? Like this, for example, this ball is in stable equilibrium. But this is not always the case, right? In some cases, for example, consider this pencil, and if you work really hard, you can balance it like this. Once it's in balance, now you can ask yourself what kind of equilibrium this is, what kind of static equilibrium this is. And you do the same thing, give it a little bit of perturbation, but this time it doesn't come back to its like stable equilibrium, but this perturbation just increases with time and just falls off. When this happens, we call this unstable equilibrium. So these two things are not the whole set, but there are certain situations where it's neither stable nor unstable. For example, consider this ball on the table, which is in static equilibrium. And if you just push it a little bit, then it doesn't come back, but it doesn't amplify this perturbation either. So we call this a neutral equilibrium. So the other thing is like, this is not always the case, right? Geometry matters, and you can consider a geometry like this. Consider your refrigerator, and there's like some force pulling it down, and there's a contact force, so it's in equilibrium. And now you are trying to give a little bit perturbation, and if this perturbation is small, it comes back to its equilibrium. But if you tilt it too much, it does not come back to its equilibrium. And from this, you can just think of like a imaginary line going through a center of gravity. And if this imaginary line is going through the base of support, which is here, we call this an equilibrium, like stable equilibrium. But if it is like here, it is not, right? So most of these things are like, intuitive. Like, for example, we all use it, right? And if you are carrying a heavy bag, you are just lifting your body just a little bit to achieve equilibrium, because you don't want your weight to be here, so you want your weight to be in your base of support. So that's like the more stable configuration. Or if you have a backpack, you lean forward a little bit because you want your base of support to go through here, and you want to be in equilibrium. You don't want to flip over. So now I want to introduce some different concepts like elasticity, stress, and strain, I think, which can be interesting. So in the previous weeks, we saw so-called Hooke's law. If you had like a spring, amount of stretch of the spring was proportional to the force. And there was this spring constant that determined the magnitude of force. And this law is actually valid not only for springs, but everything. So if you have like some system, it's like a rod, and if you hang some mass, there will be some amount of stretch. And this stretch will be within Hooke's law to a certain extent. But the amount of stretch is not only dependent on the force. So we can just actually follow an intuitive argument to see all the parameters. First of all, you can tell this total stretch is proportional to total length, because if you have like a longer rod, there will be a longer stretch. So it should be proportional to this total length, L naught. It should be inversely proportional to area, because if it's thicker, it will be harder to pull. So it will be like a less stretch. So this is like inversely proportional to cross section. And from the Hooke's law, it's of course proportional to force. So these three things. And we put the proportionality constant in this form, which is kind of funny, but it is like 1 over E. And this E we call elastic or Young modulus. So if we introduce something called stress, which is like force per unit area, F over A, and strain, total stretch divided by total length, delta over delta L0, we can say this stress is equal to strain times elastic Young modulus. Or you can write it like in this form. Sometimes in engineering, I think you'll see these kind of graphs, but this will be stress and this will be strain. And you can see what is going on. There's like a linear region. This is the region where this Hooke's law is valid. And we call this elastic region. After some point, Hooke's law is no more good for the system, and we enter into so-called plastic region. In this region, you can pull your system, but when you release, it doesn't come back to its initial configuration. It deforms. And it's also, the force is not proportional to delta L here. There is like some non-linear relation here. But if you keep pulling, there's like a breaking point, right? And that's the ultimate strength of the material. You break it after that point. So what is important to know is like, there are different kind of stresses you can give in a material. Like in this example, we are pulling, but that's not the only thing. So we can also think of pushing like this, like some sort of compression. And if you consider compression, it's also like a stress. Or you can think of like a shear stress, which is kind of like this. Imagine you have a thick book and you push it like this with your hand. You just shear it this way. And since this is on the frictional surface, there'll be a shear force like this and like this, right? These forces are acting like this. So you can write an equation similar to this one. So delta L over L0, in this case, delta L is this total deformation in this direction, and delta L0 and L0 is the total width. So you can see the thickness of book matters how much this deformation is. So delta L over L0. Now we put 1 over G, we replace this E with G, and it is the same force, this force divided by this area. And this G, we call it shear modulus. Okay, so you can give to materials tension, compression, or shear. And finally, there's like actually last kind, and in this case, we are talking about a compression from all sides, like a volumetric compression, if you like. And you can think of immersing these materials in like a liquid. Then what will be deforming will be total volume, and we say total volume divided by initial volume is equal to 1 over minus 1 over B. This minus means volume will decrease because of compression, and B is so-called bulk modulus, and this is proportional to change in pressure on the material. Okay. So these forces, like this compression, tension, shear, this is not one or the other, right? In real life, they're all acting together hand in hand, and if you like deform some material like this, for example, one side is under tension because you are just pulling this side, stretching it, whereas the other side is in compression. Let's look at some numbers. Like here, you just copy this table from your book, which is, I think, interesting. You can look at this Young modulus, shear modulus, and bulk modulus of different materials. For example, we can start with iron or cast iron. So it's like Young modulus is like some big number. You can see its shear modulus is like half as big, whereas bulk modulus is almost the same. So with the iron or steel is even better, right? Young modulus is twice as better, shear modulus is twice as better, bulk modulus is like more than twice as better. Is it more than? Almost twice as better. So brass, so you can look at concrete. Young modulus is comparable to iron and steel, but it doesn't have much shear, right? If you have a concrete and try to bend it, of course it's going to crack because concrete is not good for that kind of thing. So you can look at your bone, for example, it has like a large Young modulus, and it's also even larger shear modulus, which is interesting, and so on. I think I'm not going to solve this problem. You can work it for yourself if you like later. So like I said, if you put too much stress in a material, you start forming so-called fractures. So you just break it, and this breaking point is also characteristic of materials. Different, we know from real life also, like different materials break at different strengths. So here I also copied the table. Of course, this is like a reference, like a not absolute values, but like an approximate values or to give us an idea. So this is so-called ultimate strength of material. At what force per area is needed to break, what kind of stress is needed to break the material. And of course, the stress can be tensile, compressive, or shear strength. And let's start with iron again. You can see it's like order of the same, right? These are all maybe compressive strength is like more than 2 times better. But if you look at concrete again, let's look at concrete. Its tensile strength is, I don't know, hundreds of times less than iron, but its compressive strength is not as bad, right? It's like compressive strength is 10 times better than its like tensile strength. and its shear stress is also pretty bad. So for the concrete, you better not try to put like these like horizontal columns in your ceilings, because that's actually not as good. Or like brick. So wood, you can see wood, tensile strength, compressive strength, they are pretty much the same, but this shear stress is also pretty bad. Like if it's actually much worse than the case, it's actually better than concrete, but its tensile and compressive strength is better than its shear stress. So I think this one is probably better to build like roof, for example, and so on. Generally, something called safety factor, when engineers design some structure, they take these reference points and they put like a safety factor. What this means is they try to build it like, I don't know, let's say 10 times stronger than its like reference strength, so that its safety factor is like 10. Okay. So maybe I can give you an example and we'll finish here. Here is a conceptual example from your book, I think, which is interesting. So two walkways, one above the other, are suspended from vertical rods attached to the ceiling of a high hotel lobby, as in this figure. Okay, you have some rod, you have some bridge going through. And the original design called for a single rod of 14 meters long, like this. But when such long rods proved to be unwieldy to install, it was decided to replace each long rod with two shorter ones, as shown here. Determine the net force exerted by the rods on the supporting pin A here, which is assumed to be the same size and here, for each design. Assume vertical rod supports a mass of M of each bridge. So we are assuming this is M, this is M, this is M, and this is M. So we want to calculate the total stress on the pin A and here, and on the pin A here. Okay. So here, maybe I can start from here, right? There is some, I think, like tension here, which is what? Which is like mg because of this guy. Whereas here it is 2 mg, right? Because you have this and this, 2 mg. So on this figure, I have what? It is like 2 mg the same. This is also mg the same. But the point is, this mg has no effect on this pin. But this pin is also in contact with the bridge, right? With this guy and this guy. So there's also this force from the bridge, like here, which is mg. And here, this is also mg. But in this case, since the bridge is connected to a mass of 2 mg, right? If you look at here, this whole thing is hanging on the bridge. This is actually 2 mg. This is actually 2 mg is pulling down. So maybe I can write it like this. Let's identify all forces on the pins like this. So this is the first one. This is the second one. And the first one has like what? So, so the total force coming from the rod is 2 mg up, 1 mg down. So it's in total something like this, mg. And this is coming from rod. And there is also force coming from the bridge, which is what? This is mg This is from the bridge. If you like, top bridge. So in the second case, let's pull this guy a little bit to here. Now I have still M2 mg here. So this is from top part of rod. And there's some force down, pulling this pin down here. So there's like some mg from this bridge, but this mg also is acting on the same pin. So here is 2 mg from the bridges. Okay. So what I see here, this different design. So the first design has like some mg stress on this pin, but the second design has twice as much strength as the first one. So if your pin is weak, actually, this second design is more dangerous. And what is interesting is, I think something like this actually happened in like 1980s in a hotel in Kansas. So they decided to switch from this design to this design, and the bridge failed. And I think over 100 people died. It's some simple mistake like this. So I want to finish with like these things are actually like an engineering problem, right? How to design all these things, like considering like stress, strain, and shear, and like material properties, and there are different approaches. One approach is like using a reinforced concrete. So if you want to build an engineering structure that is like more durable, you can reinforce the material with some irons. I think we are familiar with this. And what is interesting is you can actually pre-stress the iron before you put it in your cement, and that seems to increase its durability. So sometimes maybe you see bridges like this in this structure, right? This is called truss, like use of trusses in bridges. Or like you can actually see it in like some cabins too. There's like, if you look carefully, you can see these triangles in this structure like this, like this. And the idea is this kind of structure is more durable until like shear stress, because if you have like a square, of course it can deform to some shape, but a triangle is more durable for that. Another thing is like domes. For example, domes are interesting because the concrete, as I showed you, is not good for shear, right? If you try to bend a concrete, it breaks. And it's not good for tensile stress either. It's only good for compressive strength. And what domes are doing is actually changing the architecture so that you only have, or you mostly have, compressive stress on the concrete. And thanks to this like special design, they are more durable. Like after thousands of years, these structures are still alive with this smart engineering design. Or finally, you can use a completely different approach and go with the suspension bridges if you like. So anyways, I think these are interesting. You can take a look if you are interested. And that's end for today. All right, I think I'll finish here. Seems like there are no questions. I'll see you guys tomorrow. Thanks everybody for coming.